Right, let's get started. Okay, so hello everyone, this is SeungryongKim. So this is lecture 6, but lecture 5. So today we will continue. We will move to the matrix operation and matrix inverses, which is starting up. Oh, sorry. Sorry for the noise. Okay. So yeah, we move to the matrix operation and matrix inverses. Right. So before that, let's recap what we've done so far. Yeah. So far we discussed the matrix of the linear transformation. So why you have to know that? So we can interpret our matrix AS, matrix multiplication AS, as some kind of linear transformation, right? So like this. So if the transformation T is linear transformation, there is the corresponding standard matrix A, which is defined by T of transformation of elementary matrix, right? So this is the like this. So it was the standard matrix. Matrix A consisting of the T of E1, T of E2, T of En as a column vectors. So it was the standard matrix like this. So why you have to know that? As I told you several times, we are interested in the AX equals B, right? We want to interpret AX equals B. So left-hand side, AX is kind of the linear transformation. That's why we have to study this one. So blah, blah, blah. And we also discussed one-to and one-to-one concept, one-to-one concept. One-to is related to the existence of your solution, right? And one-to-one related to the uniqueness of your solution. And yeah, like this. And we also discussed the theorem 11 and theorem 12. And one more concept was like that. If there is the pivot in every row, T is 1, 2. If there is a pivot in every column, then T is 1, 2, 1. I think this question is very, very important to check your understanding. So I want to give this proof, the proof of this statement as your homework. In fact, this question is related to your problem in your textbook 31, 32, 35 in chapter exercise in chapter 1.9. So this is additional problem in your homework too. So please check that and please try to solve or try to prove this 31, 32, 35 yourself. And I will let you know after this homework deadline. So if I give you some hint, you can use theorem 4, 8, 12 in chapter 1 to prove these three questions. So please try to understand this one. And okay. Then let's move to the chapter. Yeah, it was the geometry transformation. Right. Now let's move to the chapter 5. Okay. From now on, we will work in the matrix domain. So we will do many things in the matrix domain. So to understand this, we have to start with the matrix operation, right? But we already know several kinds of matrix operation already. So let's just briefly summarize what we have done so far. This is chapter 2.1, matrix operation. So right. So matrix operation. If matrix A is n by n matrix, that is m rows and n columns. Okay, let's write my matrix A consisting of m row and n column. Then each element can be represented by, okay, so here is m rows and n columns. Then single entry in the ith row and jth column of matrix A. For example, this is ith row, and this is maybe jth column. Maybe this one and this one. Then single entry in ith row and jth column denoted by aij in general. aij, okay, which is called j entry of the matrix A, which is called ij entry of the matrix A. Similarly, you can determine each element in your matrix A. For example, like A11 is here, A12 is here, blah 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 blah, A1M, 아니죠? Sorry. 21, M1, and there is the A12, blah 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 blah, one N, right? And last value should be AMN, looks like this. And one of the element is AI, J. So IJ entry. So this is just the definition of your matrix A. We already know that, right? Each column matrix A here is a list of m real numbers, right? So this one is just a column vector. So it's a list of the m real numbers, right? Which identifies a vector in our M space. So maybe this is the vector A1, which is in our M space. We already know that, right? So this is just definition. The columns are denoted by, right, A1, A2, A3, blah blah blah, AN, because N by M. 이상한데? M by N, 맞죠? M by N, right? So M, A1, A2, AN. The matrix is A is written as matrix A as A1, A2, AN. The number Aij is the ith entry of jth column of vector Aj, right? So here, here, jth column, jth ith entry of the jth column vector Aj, because this is Aj, right? This is just definition. One more concept is the diagonal entries in M by M matrix. A is a set of Aij. Diagonal entries mean A11, A22, A33, and they are form the main diagonal matrix A. So like this. Okay, let's suppose that your matrix A here, and each diagonal term of matrix A is A11, A22, ANM, MN, 그렇죠? MN, sorry, MN. Then this one is called diagonal entry. Diagonal entries, right? Diagonal entries. Diagonal matrix. Diagonal matrix is the n by m square matrix whose non-diagonal entries are zero. Whose non-diagonal entries are zero. So this is the specific version of the matrix, which consists of the, okay. So let's suppose that our matrix B is the diagonal matrix where when, let me use the black color. So when matrix B defined like D11, D22, Tn, while non-diagonal term is 0, like this. So in this case, matrix B is called diagonal matrix. Diagonal matrix. One example is the n by n identity matrix, right? n by n identity matrix, In. We already know In, 그렇죠? In 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, with n columns and n row and n columns, right? So one of the examples of the diagonal matrix is the n by n identity matrix. And n by n matrix whose entry is a whole zero is a zero matrix. Zero matrix. For example, zero matrix looks like this. M rows and n column and whole entries zero, like this. So this is a zero matrix. Diagonal entry, diagonal matrix, zero matrix. Right. It's very easy, right? One more thing is summation and multiplication of in matrix domain. The two matrices are equal if they have a same size, and if their corresponding columns are equal, which amounts to saying that their corresponding entries are whole equal. What does it mean? We can say that matrix A is equal to B if each entry is in A, for example, Aij, and each entry is in B, Bij. If these two entries are exactly the same and size of matrix A are exactly the same, then we can say that matrix A is and matrix A equals to matrix matrix A equals to A matrix B. So matrix A equals to A. Okay. One more thing is if matrix A and matrix B are m by n matrix, then summation A plus B is m by n matrix, whose columns are sum of the corresponding columns in matrix A in A and B. In other words, each entry in A plus B is the summation of all corresponding entries in A, B. It's very, very intuitive, right? So let's suppose that matrix A are here, A11, A12, AN, MN. And let's suppose that matrix B defined like AP, P11, B12, P, MN, then A plus B should be sum of the corresponding entries. So for example, A11 plus A P11, A12 plus P12, blah 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 blah, A N M N plus P M N. So each entry should be summation of the corresponding entries. Right, it's very easy. Question so far. It's relatively simple comparing to our previous concept, right? So comparing to the one-to-one methods like this, it's very, very easy and intuitive. So this is the scalar summation and multiplication. Scalar summation. Question. Are you clear so far? Right? Yes. Okay. Other student? No? Right. So thank you. So one more thing is that. Okay. So people down. Let me show you one example. Suppose the matrix A is for nearly 1, 0, 1, 3, 5, 2, which size of this matrix A is 2 by 3, so 2 rows, 3 columns, and matrix B defined like this. So and matrix C is defined like this. Find A plus B and A plus C. So let's do that. A plus B is summation of the corresponding entry 4 plus 1 and -1 plus 3, -1 plus 3, and 0 plus 1, 3 plus 5, 5 plus 1, 2 plus 7. So it's going to be 5, 2, 1, 8, 6, 9. Right? What about this one, A plus C? So corresponding entry 4 plus 2, 4 plus 2, -1 plus 0, 0, -3, 3 plus 1. And what about this? Which value here? 5 plus 1. 5 plus 1. 0? 5 plus? Right? It's not possible, right? Not possible, right? Because not defined, right? So because the size of matrix A and size of matrix C are different, so we can compute A plus C. Okay, this is one example. If R is a scalar value and A is a matrix value, then scalar multiple RA is a matrix whose columns are R times corresponding columns in matrix A. Or here, matrix A defined like A11, A1, A21, A12, blah, 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 AMN. Then RA is defined like RA11, RA21, R1A12, RAMN. Very intuitive, right? Like this. So, based on this summation and scalar multiplication in your matrix domain, would you like to introduce theorem 1? Algebraic properties in the matrix. Suppose that A, B, C be a matrix of the same size, and R and S be the scalar. Then we can define A plus B is equal to B plus A plus B plus C is equal to A plus B plus C. A plus 0 is equal to 0. R times A plus B is equal to R times A plus R times B. R plus S times A is equal to R times A plus RA. RA가 아니고 S times A. 그렇죠? S times A. R times S times A is equal to RS times A. RS times A. We can easily verify this by showing that the matrix on the left side has the same size as the matrix on the right hand side, that corresponding columns are equal. So first of all, let's prove this one. We can easily prove this one. Okay, let's suppose our matrix A is A11, A12, A2, A11, A21, A12, and P, P, AMN, P is equal to P11, P21, P12, PMN. Then, first of all, let's write the left hand side A plus B, which is equal to A11 plus P11, A12 plus P12, A21 plus P21, AMN plus PMN, which is equal to P11 plus A11, P12 plus A12, plus P21 plus A21, PMN plus AMN, which is equal to P plus A. Similarly, you can prove the holder things for the statement easily. Looks like this. So it's going to be the another homework. you don't need to submit this homework, but please try to prove each statement. It's going to be very, very easy and intuitive. You can prove this holder statement looks like this. 그렇죠? Like this. 이런 식으로 여러분 쉽게 보여줄 수 있으니까 여러분 이거는 한번 홈워크로 해보세요. 너무 쉬우니까. 그렇죠? One more thing is that matrix multiplication. Not a scalar multiplication, matrix multiplication. Actually, we are interested in here. When you know matrix B multiplies a vector X. Sorry. Sorry about that. And when the matrix B multiplies the matrix vector X, it transforms X into the vector Px. We already discussed here. This was discussed this one, right? So, for example, this is a vector X space, 그렇죠? Vector X space. By using the matrix multiplication with matrix B, then you can achieve new vector B times X in another space like this. This is kind of transformation, right? Linear transformation. Then, if this vector is then multiplied in turn by matrix A, okay, the resulting vector is A times Bx. What does it mean? If we multiply matrix A again here, then new vector it's going to be A, P, X like this in another space. Right? One space like that. Right? Then ABX here, ABX is produced from X by composition of mapping P and A, which is linear transformation, In other words, our goal is to represent this composite mapping as a multiplication by single matrix denoted by AB, so that A times Bx is equal to ABX. Okay, let's go back to here. So, in other words, because matrix A and matrix B are linear transformation by matrix multiplication, which was the matrix multiplication. By the properties of the matrix multiplication, we already know here is the another mapping X to the A, Px directly with matrix AB as a transformation. So we can just say that APX is going to be ABX. So in other words, if we consider the two kinds of the linear transformation sequentially, there is another linear transformation AB that directly transform vector X to this space. A, B, X space. 자, 이해갔죠? 그래서 우리가 A 어떤 리니어 트랜스포메이션을 B를 한번 곱하고 A를 한번 곱하면 우리가 아까 뭐예요? 이것 때문에 여기서는 증명 안 했죠? 우리가 A를 곱하고 B를 곱하면 이게 두 개가 리니어 트랜스포메이션이기 때문에 우리가 어떤 A, B 한 번에 A, B가 곱해지는 이런 트랜스포메이션이 있다라는 걸 우리가 쉽게 예측할 수 있겠죠? 그렇죠? 그래서 이런 A, B B하고 AB를 했을 때 A, B를 한 번에 이 스페이스로 트랜스폼할 수 있다. 그렇죠? 그래서 this composite mapping as a multiplication by single matrix AB. So we can say that A, B, X is equal to ABX. Let's prove this one. let's prove this one. Why there is such a single matrix AB from X to ABX. Let's prove this one here. Question. So far. 자, 오늘 우리가 얘기하고 있는 부분들은 사실 조금 더 쉬운 얘기들일 것 같아요. 그죠? 우리 지금까지 했던 것보다. Question or comment or whatever. Matrix multiplication equal to kind of linear transformation. Exactly. Matrix multiplication is the linear transformation. So kind of linear transformation. Any other question? 여러분 잘 따라오고 있죠? 여러분 살아 계시죠? Clear? Yes? 아, 너무 좋다. 오케이. 계속 갈게요. 네. 오케이. So, let's prove. If matrix A is n by n matrix and matrix B is n by p matrix and X is in RP space, denote the columns of matrix P as a P1, P2, and P. Well, for example, we already know matrix A consisting of A1, A2, AN, right? And matrix P consisting of P1, P2, PP, like this. The entry in X by X1, X2, XP, like this. And first of all, we already know B times X in a vector equation as B times X, 그렇죠? B times X is the X1 times vector B1 plus X2 times B2, XP times BP in a vector equation. Which is vector equation. Right. By a linearity of the multiplication by A, by linearity of the linearity by matrix A, AB, A times BX can be represented by A times X1 B1, 그렇죠? From here, 그렇죠? A times X1 B1, blah 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 X A times XP PP, then which is can be written by X1 A P1 XP A PP A P BP. Then vector APX. Okay, we can understand this. This representation. Vector APX is a linear combination of vector AP1, because this is a vector, AP1 and APP with using entries in X as a weight. X1, XP as a weight. XP as a weight. So this is another kind of the vector equation, right? This is one kind of vector equation, which is a linear combination of the ABP, AB1, AB2, ABP with the weight of X1, X2, and XP, right? Then we can easily rewrite this one in a matrix notation, like this. AB1, AB2, ABP in column vector with vector X, because this is entries, right? So we can say that ABX, because here ABX is equal to AB1X, AB1, AB2, ABP times X. In other words, multiplication by AB1, ABP, transform X into the ABX. So this one is going to be AB. So we'll prove this one later, but we can say that AB1, AB2, ABP is going to the matrix A times B. So this is a goal we want to derive. A B X is equal to B X. Okay, so let's move to the theorem one and let's define this one. It's not a theorem, it's definition. Matrix A is n by m matrix. Matrix B is n by p matrix with the columns P1, P2, Pp. Then product AB is m by p matrix, whose columns are AB1, AB2, ABP. So here, matrix A in or m by n space, then matrix B in n by p space. Then we can represent matrix B, matrix AB as a matrix A times this vector representation B1, B2, BP, right? Then it's going to be A times B1, A times B2, A times BP. So looks like this. So multiplication of matrix, we can say that multiplication of matrices corresponded to the composition of linear transformation. In other words, matrix C is, if matrix C is AB, then X to the CX is going to be the same as P times X times A times P X, like this, which should be same. So in other words, multiplication of matrices corresponding to the composition of the linear transformation. 자, 그래서 이제 여기 무슨 얘기를 하고 있는 거냐 한번만 좀 리캡을 해볼까요? 그래서 여기서부터 얘기를 해야 되죠. 그래서 이제 우리가 어떤 arbitrary matrix B가 있고 matrix A가 있으면 결국에 이 두 개의 친구들은 linear transformation이었어요. 그렇죠? 그래서 어떤 X를 B를 통해서 BX로 가고 A를 곱해서 ABX로 가면 우리는 어떤 A에서 B, AB를 통해서 1로 가는 매트리스 AB로 나타날 수 있다라는 걸 원하는 거죠. 그렇죠? 어떤 이 매트리스 곱의 컴포지션을 사용하기 위해서. 그래서 이제 AB가 X에서부터 컴포지션, 리니어 트랜스포메이션의 어떤 컴포지션으로 나타나는데 우리 이제 이런 컴포지션을 어떤 싱글 매트릭스 이제 AB라고 표현을 하고 싶은 거고요. 그렇죠? 그래서 AB를 B 곱하고 A 곱한 거를 이제 AB를 한 번에 곱한 거로 이제 표현하고 싶은 거고. 그래서 이제 이거를 왜 이렇게 되는가를 이제 우리가 쭉쭉 보면 ABX를 하면은 X1에 쭉 이렇게 가니까 이게 결국에 AB1, ABP의 어떤 리니어 컨비네이션, X로 웨이트로 한 리니어 컨비네이션 표현될 수가 있게 되고 결국에 이게 뭐냐면 ABX가 결국에 어떻게 표현되는 거냐면은 이런 식으로 표현되는 거였고 결국에 우리가 얘가 AB1, AB2, ABP가 AB라고 표현할 수가 있다. 그래서 multiplied by AB가 transform X to the ABX. 라고 표현될 수가 있는 거였고요. 그렇다고 그러면 결국에 A, B는 어떻게 표현할 수 있냐면 다시 얘기하면 A, B1, A, B2, A, B, P 이런 식으로 표현할 수가 있다라는 거죠. 그렇죠? So, let me show you example. What do we want to do? We want to compute AB. We want to compute AB, where A is 2, 1, 3, negative 5, B is equal to 4, 1, 3, negative 2. There was typo. Yeah. This one is 6, 6, 3, 6, 3. So, first of all, matrix A in 2 by 2 space, matrix P in 2 by 3 space, 2 by 3 space, right? And we already know vector matrix B consisting of the P1, P2, and P3. So let's solve AB by using this definition. 그죠? 이거 여기서 풀어보자라는 거죠. Okay, so matrix B looks like this and compute AB1. Because A is here, P1 is here, so it's going to be the 11, negative 1. We already know this one, right? How can it compute this one? Row column rule, 그렇죠? row column rule이었죠. 그래서 2 by 4 plus 3 by 1. So it's going to be negative 1, and it's going to be 1 times 4, negative 5 times 1. So it's going to be negative 1. Similarly, we can compute AB1 as A, B1, so it's going to be 0, negative 0, 13. And AB3, it's going to be A, B3, it's going to be negative 21, negative 9. Then AB, it's going to be AB1, AB2, AB3. So from each computation, you can define this one, it's going to be 11, negative 1, 0, 13, 0, 13, and 21, negative 9. 21, negative 9. Right? We can compute AB like this, like this. Okay. So let's generalize this matrix computation, as row column rule. We're comparing the AX, comparing the A. This is today's topic. So we already know how to compute the multiplication between scalar and scalar. 그렇죠? 여러분들 뭐 2 곱하기 3이 뭔지 알죠? 그렇죠? And we already know how compute 뭐 3 by vector, 그렇죠? 뭐 4 by vector, right? 그래서 뭐 4에다가 어떤 벡터를 곱하면 4, 뭐 벡터 U로 곱하면 4U 이런 건 알죠? 근데 then we have to discuss further matrix A times matrix B. 자, matrix A times B가 어떻게 계산하느냐를 이제 우리가 배우고 싶어서 이제 여기까지 온 건데, let's do that. If product AB define the entry, 더가 두 개네요. The entry in row I and row J of AB is the sum of the product of the corresponding entries from row I of A, row column J of B. 어떠십니까? It's very, very simple. So matrix A looks like this. Matrix B is here. And let's suppose that we have a matrix AB. Then ij's entry of AB can be determined by summation of sum of the product corresponding entries from row I here, AI1, AI2, AIN, and J's column or column J, P1J, P2J, P in this case NJ. Then this one can be computed by, looks like this one times this one. So A1I AI1 times A1J, AI2 times B2J, and blah blah blah, AIN times B and J. So this looks like this. Then by doing this, you can compute each element in A times B. Then you can find the final matrix AB. This is just a low column rule. There's no proof. It's just byproduct of the fact matrix multiplication. If you rewrite this one in each element, you can easily derive this rule. There is no reason. 자, 그래서 결국에 이제 우리가 A, B를 이런 식으로 계산할 거예요. AB라고 하는 거에 매트리스 AB는 AB의 IJ 번째 엔트리는 매트리스 A의 I번째 로우와 매트리스 B의 J번째 컬럼의 sum of product of each corresponding entry. 그래서 얘네들 corresponding entry 곱한 것들로 서메이션으로 표현될 거예요. 왜 그러냐? 이유는 없어요. 그러니까 이유가 없다는 게 아니라 뭐 증명할 필요는 없어요. 그냥 여러분들이 한번 아까 앞에 했던 것처럼 그냥 우리가 벡터를 매트리스 써보고 계산해보면 그냥 이렇게 돼요. 그렇죠? 그래서 얘는 이걸 계산할 때는 얘와 얘가 곱하고 다음 걸 계산할 때는 얘와 뭐 다음 컬럼이 곱해지고 뭐 이런 식으로 계산이 돼요. 그렇죠? 이게 바로 이제 로우 컬럼 룰. 예. 오케이? Let's do that. Find the entries in the second law of matrix A, B, matrix A to B, where matrix is like this, matrix B like this. First of all, what is size of matrix A? 자, matrix A 사이즈 뭐죠? What size of matrix A? 4 by 3. 그렇죠? 4 rows, 3 columns. Okay, thank you. And size of matrix B is 3, 2. Right. Then we want to know matrix AB, especially second row of matrix A. Second row of matrix A. So we want to know AB 2, 1, AB 2, 2, AB 2, 2, P. AB 2P. 2P가 아니죠. 2, A. 끝이죠, 이게. 그쵸? Because matrix B only have a 2 column, so the second row of AB just 2 value. AB 21, AB 22. 자, let's do that. So AB 21, it's going to be second row time first column. 그렇죠? Then okay, so this value can be second row times first column in matrix B. So -1 times 4 plus 3 times 7 plus -4 times 3. Right? What about this? Second row in matrix A times second column in matrix B. So it's going to be -1 times -6 plus 3 times 1 plus -4 times 2. Right? Then you can easily compute this one and this one as a value. So please solve this one yourself. 그렇죠? 여러분 뭐 계산할 수 있겠죠? 쉽게 해볼까? -4 5 맞죠? 6 3 8 9 1 그렇죠? 1 5 1. So the second row matrix AB is going to be 5 1 5 1. Similarly, you can find out the entries in AB. Similarly, right? So this is a low column rule for comparing AB. Comparing AB. Right. 3by 2 얘기하는 누구예요? 3by 2. 4by 3죠. 4by 3. 아, 이거. 아, 3by 2. 맞아. 미안해. 자, let's discuss the properties of the matrix multiplication. Let's discuss properties of matrix multiplication. Let matrix A be an m by n matrix. Let P, C have a size for which the indicated sum and product are defined. Indicated sum and product are defined. Then let's prove this one. Ah, by the way, we already know to define matrix A, B, columns of matrix A should be same as a rows of matrix B. 그렇죠? We already discussed this one. So to define to AB, to define AB, so columns of matrix A should same as rows of matrix B, right? This is a rule. Then we will discuss the properties of matrix multiplication. First one is associative law. Associative law. A times B times C is equal to ABC. ABC. And left distributive law is A times B plus C is equal to AB, AC. Right distributive law is B plus C times A, PA times CA, RAB, RAB, ARB for any scalar values are same. IMA is equal to A is equal to AIM. So this is identity for the matrix multiplication. So this is the properties of matrix multiplication. So let's prove each law, each properties. So let me prove associative law, ABC, ABC. Right. First of all, this multiplication is possible. If this multiplication is possible, because size of matrix A was m by n, we can assume matrix B is n by p, and matrix C should be p by k. So each value, row column should be same. Right here. Then let's prove this associative law. So first of all, let's say our matrix A is C1, C2, CK, 그렇죠? CK. Right. And in this case, PC is going to be P times C1, P times C2, P times K. Right. And ABC is going to be A, BC1, A, BC2, A, BCK. Right, like this, and which is going to be A, B, C1, A, B, C2 by the properties of the matrices, right? A, B, CK, K, which is going to be A, B, C, right? By the definition. This is one of the proof for the associative law. Similarly, you can prove all the things by yourself. Because we have so many things to discuss in the lecture, I will just skip each proof one. So each proof, but it's very, very intuitive and it's very, very simple. So you can easily prove this one, right? So if you can do this, so please let me know, but you can easily do that. So please prove this one by yourself. 자, 이제 여러분들은 저희가 이제 뭐 수업에서 많은 프로퍼티들을 얘기를 하고 그냥 넘어가고 있는데 뭐 이걸 사실 증명하려면 끝도 없고 이제 우리가 수업 시간에 다 다룰 수는 없고요. 너무 간단해요. 사실 이 프로퍼티는 너무 간단하니까 여러분들이 제가 이렇게 하나씩 보여주고 있는데 이런 식으로 증명하면 돼요. 너무 간단하기 때문에 제가 넘어가고 있고요. 혹시 여러분들이 좀 이해가 안 되거나 증명이 안 되는 거 있으면 저한테나 아니면 조교들한테 좀 물어보면 좋을 것 같아요. 그렇죠? In the lecture, we just used these properties based on the assumption that this theorem is already proved, right? 그래서 우리가 이제는 이런 theorem들이 already proved 됐다고 생각하고 이제 우리는 쓸 건데 여러분들 꼭 한 번씩 해보면 좋겠습니다. 그렇죠? Right. Question. Youngmin, professor, when we present vector v in Orient space, is it okay not to mark arrow on the vector? As for me, I'm confused if we in the case we often see x is color vector. Right. So in our lecture, we just represent like this as a vector. But if I represent C like this is just matrix. And if we want to represent scalar, I just use a small c. Looks like this. So there's no specific reason, but this is just like the definition in this lecture. So you can just follow this one. Okay. Will we post the proof we have to do for the homework too? Not no, it's not necessary. So the proof for the properties, you don't need to submit, but I strongly suggest you please do that. Okay. Right. Other question? PDF? 렉처 노트? 그쵸? 렉처 노트. 맞아요. 렉처 노트는 그쵸? 힘들어요. 표현하기가 이게 타이핑해야 돼가지고. 네. 그래서 거의 지금 볼드로 돼 있을 거야 아마. 그쵸? 볼드. 예시가 없나? 볼드로 돼 있죠 거의. 그래서 볼드가 벡터로 이해해 주시면 돼요. Yeah. So in our lecture note, I just to represent the vector in a bold representation. So please remember. Right. Let's discuss another properties of the matrix multiplication. If matrix AB is equal to BA, we say that matrix A and matrix B commute with one another. 자, AB commute with one another. Here's a warning that in general AB is not equal to BA. It's very, very important rule. So when I study matrix in my high school, it's very, very important statement. AB is not equal to BA. So it's very frequently solved the problem in exam. But I just heard you did not study the matrix in your high school, so let's just remember AB is not equal to BA in general. 자, 이거 제가 왜 얘기하냐면 사실 이거 저는 7차 교육 과정인데 7차 교육 과정 때는 이게 AB 행렬 배울 때 수능에 맨날 나왔던 게 이거예요. AB 뭐 이렇게 맨날 나올 때 AB가 BA랑 같냐 안 같냐가 맨날 나왔었는데 뭐 이게 항상 같지 않다라는 인체널을 맞는 건데 여러분들 혹시 그 행렬 안 배운 친구들 이걸 혹시 너무 처음 보는 것 같아서 한번 얘기를 해봤습니다. 그렇죠? And cancellation rules do not hold for the matrix multiplication. That is AB, AC. If AB and AC, then it is not true in general. B is equal to C. B is equal to C. Why? If matrix C is the why? Like this. If AB, AC is AB and AB equal to AC and AC is equal to 0, then if we assume matrix A is the 0 vector, then B is not equal to C. So in general, B is not equal to C. Not true. If a product AB is the 0 matrix, you can't conclude in general that either A is equal to 0, B is equal to 0. So even though AB is not 0 matrix, we can generate the 0 matrix. So we can't conclude in general that either A is equal to 0, A is 0 matrix, or B is 0 matrix, right? It's just the warning. Yeah, one more thing is that power matrix A is that if matrix A is n by m matrix and k is a positive integer, AK denote the product of k copies of matrix A. So AK can be represented by 8 times 8 times 8 times. So finally k times multiplication. This is very similar to like that. If we compute the A to the 3, it should be A times A, 2 times 2, 그렇죠? Right? 2 times 2. And if matrix A is non-zero, if X is in orange space, then A times K is the result of left multiplying X by A repeatedly K time. What does it mean? AK times X is going to be 8 times 8 times 8 times AX. K times, by definition. Right? If K is equal to 0, then A0X should be X itself. Why? Because A0 can be interpreted by identity matrix. So it should be X itself. So this is similar to like this. Okay. In this definition, if we want to compute A0, it was just 1, even though any scalar values are here, right? Similarly, if we want to compute matrix A to the 0, then it's going to be identity matrix. 그래서 여러분들이 우리 스칼라에서 했던 것처럼 거의 유사하게 매트릭스에서도 parts of the matrix A가 정의가 된다. 그렇죠? Right. And one more thing is that the transpose of matrix A. Given on n by n matrix A, transpose matrix A is the n by m matrix denoted by A transpose, whose columns are formed from the corresponding rows of the matrix A. So does it mean? Okay, let's suppose that we have a matrix A whose size was n by n, then A transpose should be n by m matrix, where each column formed from the corresponding rows, and another column coming from corresponding rows like this. This is definition of transpose matrix A. It's very, very simple. For example, your matrix A is 2, 1, 3, 2, 0, 1. Then A transpose is going to be 2, 1, 3, 2, 0, 1. Here are same. So this is the definition of the transpose of matrix A. This is the definition, right? final theorem in chapter 2.1. Let matrix A and B denote matrix whose size are appropriate for the following sum and product. Then A transpose and transpose of matrix A is going to be matrix A itself. And transpose of matrix A plus B is going to be A transpose plus A B transpose. Transpose of matrix A times B is equal to B transpose times A transpose. And for scalar R A transpose is going to be R A transpose. This is another properties of matrix A. This is final homework. Right. How can I prove this one? It's very, very easy. So let's suppose here. We can easily prove this one like this. So let's suppose that matrix A consisting of the A12, A21, and AMN. Then A transpose is going to be A11, A12, A21, ANM. Then A transpose of transpose is going to be A11, A12, A21. Then left hand side and right hand side same, so we just prove this one. Similarly, you can do that. 안 할 거예요. 여러분들이 이런 것들은 여러분들 꼭 해주세요. 알았죠? That's it. Question. In chapter 2.1, we discuss some properties of the matrix and matrix multiplication, right? Why do we have to know that? So from now on, we will work in the AX is equal to B in matrix domain, and we will solve this kind of linear system in a matrix with a matrix operation. So in the following, we will derive row reduction algorithm in a matrix domain again. Then you can easily solve your linear system in a matrix domain. 자, 그래서 이제 우리가 매트릭스 도메인을 옮겨갖고 뭐라고 싶은 거냐? 우리는 항상 결국에 AX 플러스 B 리니어 시스템을 푸는 거에 관심이 있다는 거고, 자, 이제 우리가 매트릭스를 완벽하게 이해한다면 뭐예요? 그냥 우리가 어떤 로 리덕션 알고리즘과 같은 그 리니어 시스템 솔버를 이제 매트릭스 도메인에서 우리가 정의를 내려버릴 거예요. 그래서 매트릭스 오퍼레이션으로 풀어버릴 거죠. 그렇죠? 그럼 우리가 훨씬 더 시스테미컬 웨이로 이제 우리가 리니어 시스템의 솔루션에 대해서 얘기를 할 수 있게 되겠죠. 그렇죠? Question so far. Question. Question. No. Okay, what time? 6:03. Okay. Let me take 5 more minutes to start chapter 2.2, inverse matrix. 자, matrix inverse. It's very, very simple. So to understand the matrix operation, you can consider the corresponding how to say the scalar properties of the scalar operation. So we are interested in matrix inverse, right? Then let's think about the scalar inverse. So this is the inverse in the algebra. So let's consider this one. So we have a scalar value 5, but we want to generate 1 by multiplying some equation, some values, and we also want that by multiplying some values in front of 5, we also make 1. So the question is, which value to satisfy this statement? In this case, which scalar value can satisfy this statement? 5 times what is equal to 1? Right, exactly. 1/5. So 1/5. Then What is 1 over 5? 5 to the negative 1. 그렇죠? 5 to negative 1. This is inverse in algebra. Then, what are inverse in matrix? What are inverse in matrix? Okay, similarly, we have arbitrary matrix A, and we want to find out another matrix that make this matrix A as an identity matrix, and this matrix can make arbitrary matrix times A as an identity matrix again if matrix A in R n by n space. Now, question is how to find out inverse of matrix A. This is topic of chapter 1.2. Chapter 1.2. Okay. Let me do one more page. N by N matrix A is said to be invertible if there is the N by N matrix C such that C times A is equal to IN and A times C is equal to IN. In this case, C is inverse of matrix A and uniquely determined by A, because if B were another inverse of matrix A, then P times BIN should be P times AC, which is equal to PA times C, and PA should be IN, then IN times C, so which is going to be C. So if P is another inverse of matrix A, this matrix B is equal to C. So in other words, this inverse of matrix A is uniquely determined. So we represent this unique inverse as a to the negative 1. A to the negative 1. So from now on, we'll define inverse of matrix A as a to the negative 1. So in other words, inverse of matrix A times A is equal to IN, and A times inverse of matrix A is IN. So this is a definition of the inverse of matrix A. Then we call then if there exists the inverse of matrix A, we call matrix A is said to be invertible. So this is the definition of the inverse of matrix A, right? All right. So this is the chapter 1.2. In remaining part, we will discuss how to find the matrix invert of your arbitrary matrix A. Okay. Question. Question? No? Right. So yeah. The question by 정윤? 중간고사 midterm exam. Right. So we will take a midterm exam, but the midterm date is not determined yet. So I will let you know. But we will take a midterm exam maybe end of April. So I will let you know soon if it is determined. So, 곧 알려줄게요. Other question? No? All right. So please remember that we have a homework 2, which is due on April 14. So please try to solve yourself. And today we have so many properties, right? We have too many properties. So please try to derive or to prove by yourself. It may be easy, right? Right. So any other question? No? 무건학생 블랙보드 올라. 네, 블랙보드에 올라온 문제들만 풀어도 내면 돼요. 알겠죠? Okay. That's it. No? Okay. All right. So this is end of today's lecture, and this is end of this week. Thank you very much, and see you next week. 여러분들 오늘 고생하셨고요. 우리 다음 주 화요일 날 다시 보도록 합시다.